Okay, this is just going to be a brief explanation of what we mean by force fields in physics. So please turn around and watch the lecture. I want to see the back of anybody's heads while I'm lecturing. So look up here. Okay, there's plenty of places to sit. All right, so we're going to talk about what is a force field. What do we mean by a force field? And then we'll specifically talk about electric fields today. And then we'll develop an equation, Coulombs Law, that will allow us to do some pretty simple equations here. Now, what is a force field? I mean, we hear this term, force field, used in science fiction all the time. But there really are force fields. Science fiction likes to use the vocabulary of science in their stories, and sometimes they actually do a pretty good job. But quite often it's kind of fantasy dressed up as science. So you have to be careful about that. But here's the thing. We're going to deal with three kinds of force fields in physics in this class. Okay. Gravity, electric gravity fields, electric fields, and magnetic fields. Now these are all force fields. And what we mean by them is that gravity, or the electric field, or the magnetic field, they can apply forces to things that they're not touching. Just by being just by being close to something, you get a force on you. And we call that, the effect something has on the space around it is we call a force field. Like we have a planet. Here's Earth. Okay. Now the Earth has a gravity field. And what we mean by that is that if I have another massive object nearby, it applies a force to my massive object. Of course, my massive object applies an equal and opposite force to the Earth. But if we want to know, okay, what is the gravity field of Earth on this object? Well, we basically do this. Why does the Earth apply? What am I trying to say here? What characteristic does this object have that allows the Earth to apply a force to it? This object has mass. And we get a force on it. Okay? So there's the force acting on it. And so what we do to describe a field is we say, how much force do we get for that amount of stuff? So we're going to call this the gravity field, and we call it G. Now we actually did this earlier in the year, but it's been a long time, so I'm going to review it. And what did we say G was? Well, it's the force of gravity divided by the mass of my little object right here. And this tells you what the Earth's gravity field is like. And it has units of newtons per kilogram. So it's the force I get because my object has mass and because it's close to the Earth. So the Earth actually creates a force field all around it. And what we mean by a force field is that if you're in the field of the Earth, and it's a three-dimensional field, not a field like, where you grow wheat and stuff, but a region of space around the Earth. If you're close to Earth, it's going to exert a force on you if you have mass. Okay? And we call that a gravity field. And it is a force field. Now, we know what there is an equation for the gravity field because there is an equation for a force between two massive objects. Do you remember? It was big G times the mass of the Earth times the mass of my object over r squared, where r is the distance from the center of the Earth to my massive object. And then we divide that by the mass of my little object out here. I'm using this little object to measure Earth's gravity field. And of course, this little mass canceled out. And so we said that Earth's gravitational field was equal to Gm over r squared. If you cancel out all the units here, you get newtons per kilogram. Now what's the direction of it? Because this is a vector. The direction of a gravity field is down. Or you could say, instead of down, you could say towards the center of the Earth, right? Now what is the Earth's gravity field near the surface of the Earth? I mean, for us, for you, what is the Earth's gravity field for all of us? 9.8. It's 9.8. You can call it either newtons per kilogram, or you can call it meters per second squared. Because a newton per kilogram cancels out to be a meter per second squared, okay? But you have a region of space around the Earth that applies forces to objects that have mass. How much force per unit mass? That's the gravity field, okay? Now let's talk about electric fields. And then we're going to talk about magnetic fields probably on Friday. Okay, so electric fields. Well, the electric field is, in some ways, it has something similar to it. It's the force. Well, I didn't write this down, but a gravity field. What is a gravity field? It's the force applied to an object because it has mass. Right? If an object is in a gravity field, it'll feel a force because that object has mass. Well, an electric field is the force an object feels because it has, what do you think? It's not because it has mass, because that would be gravity. Well, yeah, you're on the right track there. Because it has a, I'm just going to call it a net charge. You know when you rub a balloon on your head, it gets a static electric charge? You ever done that? Rub a balloon on your head and it sticks to the wall? Where does that force come from? Or you take socks out of the dryer and they stick together. Well, that's because those objects have a very tiny net charge. And that net charge creates an electric field around it that allows it to apply apply forces to other objects that have a net charge on them. Okay, and so for example, let's say I have a balloon. And so here's my balloon. And I've got a bunch of positive, let's say I deposit positive charge on the surface of the balloon. Now, what this is going to do, and I'll call this capital Q. Now, this is kind of like the Earth. Think about this balloon as being kind of like the Earth. And then what I do is that I put a little charged object nearby. Let's say I put a little positively charged object, and I'm going to call that little q. Remember how I called this big M for mass of the Earth? This will be big Q for the charge on my balloon. And then I put a little object nearby, and a force will apply to them. Now, what do we know is true about like charges? What did we say the other day about like charges? What do like charges do? Repel. They repel each other. Now, with gravity, there's only one kind of gravity. There's only one kind of mass, and it's all attractive. All massive objects attract other massive objects. Okay? But with electric charge, there's two kinds of charge. There would be, positive charge and what we call negative charge. Unlike charges attract, like charges repel. It would be as if, if you want to make a zillion dollars, come up with anti-mass or negative mass. So if I had a baseball made out of negative mass and I released it, it would be repelled by Earth's, it would fall up. But there is no such thing. But there is such a thing as positive charge or negative charge. Positive charge is carried by the protons, negative charge is carried by the electrons. But these two guys are both positive, so they apply equal and opposite forces to each other. if I measure this force in newtons and divide it by this charge, Q, I get what's called the electric field. And I make it capital E, but with a vector hat on it. Because what else did we use capital E for earlier this year? We said E was mechanical energy. But energy is a scalar. It doesn't have a spatial direction associated with it. But electric field does. Electric field is a vector. So if you see a capital E with a vector hat on it, that means, hey, we're talking about a vector quantity. It's the electric field. What units does it have? Newtons per Coulomb. Okay. And notice that it's very similar to lowercase g. Here we had newtons per kilogram, but with electric field we have newtons per coulomb. Okay? So it's a region of space around this balloon. Now sometimes we draw what are called electric field lines. If I put my positive charge here, it would get pushed away. And then I can connect all the little arrows. Like let's say I put it here, it would get pushed this way, right? But if I put it here, it would get pushed this way. If I put it here, it would get pushed this way. And so I just connect them all, and I draw what are called electric field lines around my charged balloon. Okay? So you might see things with electric field lines. We'll talk a little bit more about field lines later. What if I had two charges like this? What is the magnitude of this force? Now we're going to get to Coulombs Law. Coulombs Law. Named after a guy named Coulomb, who figured this out. And what he said is, hey, the force, and let me zoom out a little bit so you can see everything here. We have, with massive objects, we have a force of attraction. And the gravitational force, and let me rewrite it up here. Force of gravity was equal to big G times m1, m2 over r squared, where r is the distance between my massive objects, right? And anybody remember what big G was? I should give you extra credit if you can just remember it.
Universal gravity.
Yeah, universal gravitational constant, but what's its value? Do you remember? Negative 11. Well, it was a group effort, but no, that's good. You guys remember. That's very impressive that you remembered that. G is 6.67 times 10. Am I still on screen? Yeah. To the negative 11. Now, what units does this have to have? Well, what units do we want to end up with? Force of gravity is measured in newtons, but what do I have to cancel out? I got to cancel out this meters squared, right? On the bottom, so I'll put a meter squared on the top. And then what is this? Kilogram squared on the top. So I'll put a kilogram squared on the bottom. And that way the units cancel and I end up with newtons. Because that's what force is measured in. Now look how tiny this number is. Okay, it's big to write down. It's big to write down, but it's tiny. 10 to the negative 11. If I put 1 kilogram of mass 1 meter away from another kilogram of mass, the force of attraction between those two massive objects is 66 trillionths of a newton. It's hardly noticeable. The force of gravity is weak. But it turns out that if I have two charged objects like this balloon and this little charge right here, there is an equation that looks just like the equation for gravity. We'll call it the electric force, F sub E for electric. Can you see that? Should I zoom in? Okay, the electric force is going to be equal to, well, if I make one charge, I'll just call it Q1. If I've got 2 point charges, Q1, if I make Q1 bigger, I get a bigger force. If I make Q2 bigger, I get a bigger force. So let's say I've got like here's Q1, and here's Q2, like right here, they're going to repel each other, right? And so what I'm doing is I'm figuring out the magnitude of these repulsive forces. They're equal and opposite. And I've got a distance between them. I'll call that R. And it turns out to be a function of R, 1 over R squared. That is, the farther apart I make these charged particles, the weaker the force of repulsion is by the square of the distance. Just like gravity. Now, by the way, this is a property of three-dimensional space. If you have something that's spreading out in three-dimensional space, its strength will get weaker by the square of the distance. Whether it's gravity, if it's twice as far, you only have 1/4 as much force. The electric force, if you put them these two charges twice as far apart, you only have 1/4 the amount of electric force. My voice, what I'm doing here, actually if we were outside and there were no echoes off the wall, that kind of distorts things a little bit. But my voice is spreading out in three-dimensional space. And so it gets weaker by the square of the distance, the intensity of the sound I make. If I have a candle, if I light a candle and let that light spread out in three-dimensional space, the intensity of the light gets weaker by the square of the distance. If I make it 3 times as far away, the light is 1/9 as strong. So it's a square of the distance. If I make it 10 times farther away, it's 1/100th. This is why, like way out in Pluto. Pluto, I forget, I think it's 35 times farther away from the sun than the Earth is. So what's the intensity of sunlight at Pluto? It's 1 over 35 squared. I don't know what that would be, but it's, 1,000th the intensity of light for Earth. Now, by the way, that's still bright enough for us to see. I mean, that's brighter than a full moon. So if you were on Pluto, you'd be able to look around and see. It would just be very dim. It'd be like twilight here on Earth. Okay. But anyway, getting back to this, that's all you can do is change the charge and change the distance between them. So guess what we need? Well, with gravity we had big G, right here. Well, with the electric force, we're going to have what's called K sub E. Or we'll just call it little k. We don't need the sub E on there. Now, this is a constant of nature. It is the electric constant. And it's very different than the gravitational constant. Because let me show you how big this is. This is a big number. The electric constant is equal to 9 times 10 to the 9 newtons of force. Now, what are the units going to be? I mean, this is Coulombs Law right here. I want to end up with newtons. Now, what do I got to cancel out? I got Coulomb squared on the top, so I'm going to put Coulomb squared on the bottom. I got meter squared on the bottom, so I have to have meter squared on the top. So it's Newton meter squared per Coulomb squared. Okay. Now look how similar that is to the gravitational constant. This was Newton meter squared per kilogram squared. So here we're dealing with mass. With the electric constant, we're dealing with charge. This is huge. If I put an object with 1 coulomb of net charge, if I made this 1 coulomb of charge, and I made this 1 coulomb of charge, and they were 1 meter apart, the repulsive force would be 9 billion newtons. It would be huge. A huge force. Now let me tell you how big this force is, and then we'll be finished. Did you ever see the movie Harry Met Sally? Okay. It's an old 80s romantic comedy. It's a good date movie, so, If any of you ever get a date, you can watch Harry Met Sally. But good luck with that, some of you. All right, now, so here's Harry, played by Billy Crystal, and here's Sally, played by Meg Ryan. And let's suppose I had a magic wand. And on the magic wand, I was able to give Billy Crystal 1% more protons than electrons. Just 1% more. Like, we're all electrical beings, right? We're all made out of protons, neutrons, and electrons. So we're made out of charged particles. What if I just added 1% to his positive charge, and I added 1% to Sally's charge? So now they both have positive charge on them, but only 1% more than they already had. 1% more than their negative charge. What would the repulsive force be between Harry and Sally if they were standing 1 meter apart? Well, I don't have time, but if you do the math, and we actually do the math in AP Physics, the repulsive force would be huge. It would be greater than the weight of the earth. You would not want to be anywhere near Harry and Sally if I were to do this. The repulsive force would be so great that they would be instantly vaporized as they compressed against the air. They would release so much energy that it would be greater than a thermonuclear weapon going off. It would wipe out the city of Clovis and Fresno together. It would be bad. It would leave a huge crater in the earth. It would kill us all. The electric force is huge. Now, here's what I want you to do. Let me zoom all the way out. Oh, there's one thing I got to add. And I already told you this before, but I'll squeeze it in right here. One proton has 1.6 times 10 to the negative 19 coulombs. You need to know that. One electron has negative 1.6 times 10 to the negative 19 coulombs. You'll need that to do a couple of the problems. But you can do the first 4 problems of assignment 6 with this equation. This is Coulombs Law. And it expresses how strong the electric force is. And you divide that by the charge on one of the objects, you got the strength of the electric field. Okay, that is all.